Okay, the plan for today, let me just give you an idea how we finish up the course. Today is not really it's not really exactly the end. For this Friday, okay, sorry, forgot to put the dates. Friday, April 5th. Okay, this Friday, 2 p.m. to 4 p.m., Leçon B. That's the makeup lecture. Basically, I cannot finish everything about the Hoare logic today. I want to do things properly, otherwise you'll be struggling for the exam. I'll make sure I cover that smoothly. So today I'll finish hopefully everything until the loops, and then on Friday we're going to continue with the topics for the loops. And there's also one more topic that both sessions agree we're going to cover more deeply, which is about how to use agents. So Friday the lecture is going to be 2 hours. Okay, so make sure eat your lunch before Friday, before you come. Take your nap before you come. So we're going to cover for 2 hours. Okay? Any questions? Just about, yeah.
Will there be a recording on Friday?
No guarantee. If you don't come and I don't record, you're in trouble. Huh? Yeah, maybe have your friend come to take notes for you. Okay. Yeah, all I can say is the lecture is important. I'll try to record as usual, but sometimes technology might fail, right? Either by accident or intentionally. Right? Either way. I'll try to record. I wouldn't say I wouldn't record. Okay, guys, let's go back to where we should begin. Okay, Hoare logic. Basically, last time we just gently introduced you to some motivating examples. You're given basically implementation and also pre and post condition. We don't really talk about invariance, but invariance is also important because you can think about the class invariant is like the post condition for every feature, so just part of it. Okay. So now, this is pretty much where we ended up with last time. Okay, can anybody, just at this point, explain to me how you understand this notation over here before I review it? Anybody? Anybody want to try? Don't be afraid to be embarrassed, that's okay. You're getting somewhere. Okay, at least we know Q is a precondition, R is a postcondition, S is the implementation, right? Yes.
So Q is a precondition, S is the implementation, R is the postcondition, and Q is after being optimal.
Okay, sounds like a weakest, right? Okay. Okay, but what's the meaning for this triple here? What's the meaning? Remember, this whole syntax over here is a Boolean predicates, which means this syntax here can be either proved to be true or can give me one counter example, right?
The preconditions by applying the code or specification in S, this whole double will be true if that results in R.
That result is going to satisfy R, right? Okay, let me just say that again. So this whole triple here is going to be a Boolean, either true or false. It will be true if and only if you start with a state that satisfies the precondition Q. And then you try to execute the implementation S. The implementation is going to be, number 1, terminates, and number 2, upon the termination, is going to establish the postcondition R. Okay, that's the answer, in case we ask you in the exam. Okay, that's more like a definition type of question. But now we want to know exactly how we can prove this. In order to prove this, we have to do some calculation called the weakest precondition. Okay, that's something we're going to focus today. Okay. Let me just do one more diagram to summarize what we said last time. So conceptually, you really want to know exactly how to understand this. Okay? So this is the most important equation abstractly you have to understand. Okay, I'll try to draw things from scratch. Basically, you can think about we got some equivalence, which means if and only if. Okay? When you try to, okay, you are given some IFO code with precondition, postcondition, and also the implementation. Okay? Somehow, you have to formulate your program into a Hoare triple like this. Okay? You got a precondition here, implementation, and postcondition. Okay? For example, let's say if you have this. Let's say this is a program you are given. Don't worry about the diagram beside. Okay? I just want to show you quickly. For this one, you can see I can simply put I larger than 3, which is the precondition, and also implementation is exactly over here. I is assigned to I plus 9. And then the postcondition we're expecting would be I larger than 13. That's how you formulate. The formulate process is very easy just by copying and pasting. Okay? So now, in general, if you have this particular form, how to understand exactly what we are trying to prove? Let's do the following, okay? So now, thinking this way. First of all, let me start with the post-condition. Post-condition is really something you would like to establish at the end. So you can think about this circle over here is going to be the set of value that's going to satisfy R. Eventually, we want to end up in a state that is going to satisfy everything like this. Okay? That's the post-condition we are aiming for. And we are also given some implementation over here. You can think about eventually we want to make sure by executing S is going to terminate in a state that's going to satisfy R, right? S over here. So now, given the blue and the pink, there is a way for calculating what should be the weakest set of pre-states that will allow you to start with and then end up with a post-condition satisfying states. So what do I mean? Basically, you can see there's a precondition calculation over here called WP. We're going to go over that for sure today in details. So given the statement S, given the post-condition over here, we can calculate just WP. By the way, WP is just another predicate, which is also either true or false. You can think about given the blue, given the pink, we can somehow calculate another circle being a predicate. It's basically the WP for S and R. Okay? The orange is what you said to be optimal, but optimal is not very precise. Weakest. Weakest in the sense that if you start your program from any of the states inside this particular WP predicates, and then you try to execute S, it's guaranteed it's going to end up with a state that's going to satisfy R. It's guaranteed. Okay? One missing piece of the puzzle, which is the Q over here. The Q over here is really the precondition that the designer chose to give. But we don't know yet if the precondition is really correct or not. So now, how can we be sure? Because we know that every dot inside the WP circle is guaranteed to satisfy the postcondition at the end. So now all we want to make sure is, logically, the green circle over here for Q is going to be just a subset. Right? That's why you see the implication over here. Okay, that's the conceptual model you want to have when you try to do WP and also program verification. Any questions? Okay, so now for the rest of the lecture, okay, can anybody just make sure I don't run over time beyond 2 p.m.? Okay, I should only go until 2 p.m. and then we're going to talk about the exam. If I run over time, you don't have any exam tips then. Okay, make sure you remind me. Okay, okay, so now we have this. Okay, so that's kind of the implication we're going to prove. But now the question is, how exactly do we calculate this WP? Okay, we're going to talk about it. Okay, so now let me give you a little bit example over here. So now if you look at this particular program over here, as we said, we have formulated into the Hoare Triple over here. And then in this case, you can see I larger than 3 is the actual precondition, right? It turns out the weakest precondition, you can see I is assigned to I plus 9. And also I larger than 13 is over here. It turns out that WP, as we'll show you how to calculate, WP is simply I larger than 4. Okay, we'll see exactly how to calculate this. So now all we want to ask is whether or not this particular precondition, which is I larger than 3, is a subset of I larger than 4. Is it? Is that the case? If you don't think that's the case, give me a counter example. 4, right. That's how you disprove it. No, because when I is equal to 3, it is going to, right, it's not going to satisfy, right? Oh, sorry, I is equal to 4. Oops. If you try I is equal to 4, then it is going to satisfy that, but this is going to be false, right? Okay, that's just one example. Okay, and then on the other hand, if you are given another program, if you give it another one, so again, you can formulate it. You can say I larger than 5. That's a precondition. And also I is assigned to I plus 9. Okay, implementation. And also I larger than 13. Okay, that's a formulation. Always the first step. Formulate Hoare Triple first. And now, Once you calculate the WP, it's the same pre-implementation, also the same post-condition, so the same weakest precondition. In this case, it's going to be I larger than 4. So now, is I larger than 5? Does that imply I larger than 4? In this case, yes. So that's how we prove it. Okay, 3 steps always. Number 1, formulation. Number 2, calculate the WP. Number 3, prove or disapprove. The precondition you have implies the WP you calculated. 3 steps. We might give you the first step in the exam, but make sure it's not guaranteed. You want to make sure you know how to formulate it. Guys, any questions? Okay, if no, we're going to talk about exactly how you can calculate the WP. One more thing to draw your attention quickly. So when we talk about WP, right, weakest precondition, you always have to give a program S and then some postcondition over here. Okay, let's talk about the structure you're going to encounter into. Okay, so the R over here is basically going to be the postcondition, which is the predicates. And one thing you have to be very careful about. Remember in IFO, in the postcondition, you can actually do a relation between the pre-states and post-states by using the O keyword, right? So now here you have to distinguish between pre-states and post-states. Okay, that's something we'll see. Okay, so the postcondition itself is not too bad as long as you're clear about the pre and post states. Okay, and the implementation over here is the program. So we're going to talk about different cases. Basically, you can think about the program structure here as a composite, a recursive. What you're doing now for lab number 5 is a composite, right? For the expression language, the same over here. So what can be the base case? Well, you got assignments, right? You have recursive case, you got if then else. Also, you can have one statement followed by another. Okay? And also, you got loop. You got from, until, loop, and also end, right? So these are the 4 things we have to talk about today. We may not reach number 4, but 1, 2, and 3 for sure. Okay? Once you get number 1, 2, and 3 done, you can already verify some simple programs. Okay? After number 4, you can do basically any program. Okay? That's about the big picture. Okay? So now let's go back to the first rule that we briefly talked about. I want to give you a little bit more insight about the first rule. That's really fundamental. Okay, so that's about, okay, so these 4, okay? So now if I go to the first rule, one more thing to say, since we're going to do the WP calculation on the paper, so we don't really use the O keyword just for simplicity. So every time you have to use O keyword, just use X0, okay? So rather than saying old X, you will say X0, okay? Just for the pre-states. Okay, we're going to see example. So now this is the first rule. You can see now we have some post condition over here, and we have some assignment over here. That's the program. That's the simplest case. So now what should be the corresponding WP? Right? It's going to be what we said last time. It's going to be basically the same predicates with the same structure. However, every occurrence of X is assigned to E. To be more precise, every occurrence of the post states value of X is going to be replaced by E. Okay? So now, let's see one example. Do I have one example here? Okay. Let's see over here. So now, if I have the weakest precondition, let's say, if I have a WP, okay, X is assigned to X plus 9, X larger than 13. Okay, let's talk about this one specifically. First of all, tell me something. When I say X is larger than 13, this X over here, are we talking about pre-states or post-states? Post-states, okay? Okay, so now tell me something here. We got 2X over here. Do they both refer to the same pre-state or post-state? Tell me. Which one is pre-states? Okay, you can think about This guy here is to say whatever x used to be, use that as the plus 9, and then assign that to the new x, right? Especially you can think about this as a pre-states. One more thing to ask you about. When we talk about precondition, when you specify precondition in IFA, or just think about precondition in general, when do you check precondition? It's before the feature body is executed, right? So that means every value you refer to in the precondition should be pre-states only. There's no post-states. So now here's a problem. If you look at the post condition over here, okay, it's talk about post states, right? If you talk about precondition over here that we want to check, you talk about pre-states only. So you can see pre-state and post-state, we talk about two different domains over here. How do we transform from one to the other? You got to do some substitution, okay? Basically, you're saying that I want x larger than 13 to be true in the post states. However, the post state value x over here is the same as the pre-state x plus 9. So that's how I can do the substitution. So now I can simply replace this. I can say x0 plus 9. So which means writing x, which refer to the post state value, is equivalent to just writing x0 plus 9. Because the implementation tells that we're going to do the post-state value as x0 plus 9. Okay, once you have done that, you can do simplification. You got x0 larger than 4. So this is the weakest precondition. So now in the precondition, you don't have to say x0 larger than 4 because every state, every variable in the precondition is just a pre-state. So you can just get rid of x. So that's why you just want to be careful. Okay, when you do the WP calculation, you want to be clear about which variables are referring to the pre-states and which are referring to the post-states. But when after you calculate it, no x0 should be there. Okay? Everything should be just the original form. Okay, this slide here, I'm just trying to give you some more intuition about this particular rule. Okay, and after this, everything will be kind of recursive. Everything. This is the only base case you have. Okay, and in this particular base case, we're just doing substitution. Okay. Replace every occurrence of the post-state value by the pre-state value expression, okay, according to the implementation. Any question about this? If no, let's do a little bit exercise. I believe we got some example over there. We can do it. And then in the exam, there is a particular way of presenting proofs you have to follow, which I'll show you. Okay. Basically, you want to go from one expression to another. In the middle, you have to justify exactly which WP rule you're using. Okay, I'll show you. Okay, so now this one's done. Okay, now you want to do this one? What is the weakest precondition for a program? Let's say x is assigned to x plus 1, incrementing. And then to establish the post condition, x larger than x0. Well, you can see now the post condition over here does refer to the pre-states and post-states, right? We're saying that the post-state value x is strictly larger than the pre-state value x0. So now, what would be the weakest precondition? I heard true. Okay. What do you mean empty nothing? Well, we want a predicate, right? Empty is not a predicate. You meant false? So let's see this. Yeah. Okay. That's okay. We're just helping you to get started. Okay. So now what we want to do, let me write it out. Okay. First of all, you want to formulate this question over here. You want to calculate the WP for, I'll write it down and then I'll switch to iPad. We're trying to increment x to establish x strictly larger than x0. This is something you should be able to write. Agree? So now, if you want to show the step for WP calculation, this is how you're going to present it. You're going to say this is going to be equal to, and then you're going to put curly brackets. It can be square brackets, it doesn't matter. But you're going to justify the step over here. Okay? I'm going to say it's going to be the WP rule for assignments. Okay? It's going to be x strictly larger than x0, where every occurrence of x is going to be replaced by x0 plus 1. Agree? Okay, so now what would that be? X larger than, okay, in this case, let me just do a little bit more for you. And over here, let me just, over here you can say substitution. And then it's going to be x0 plus 1, right? X is replaced by x0 plus 1. Larger than x0. What is that? True, right? Because, well, if you cancel out, 1 larger than 0, always true. So that means the weakest precondition for x is incremented to establish x larger than x0 is true, which means it doesn't matter what x you try. If you try to increment something, of course it's going to become larger. Okay, we're just trying to verify the common sense, right? But you want to get used to the format. Guys, are we okay? That's the very first example. Okay, so notice that most likely TA will be reading your proof. To really make it more convenient and easier for the TA, you really want to present this kind of style. So it's actually rigorous for the TA to really be convinced you're presenting the right thing. Okay? Don't invent any format yourself. Okay? You start with something, and you want to say it is equal to another equation, but this is a justification. Okay? You're going to do that as detailed as possible. That's our first example. We'll do more. Any questions? Yes? What do you mean? Which ones? X0? Well, true in the sense that, so that means the WP is true. That means any x being incremented will become larger. For example, if x is minus 1, and then you say increment, it becomes 0. 0 is strictly larger than minus 1, right? If I try x is 2, after incrementing, x becomes 3. 3 is strictly larger than 2, right? Doesn't matter what x value you try. So that's why the weakest precondition is simply saying under what circumstance you can execute this implementation and guarantee to satisfy the postcondition. In this case, it's just going to be any input value. There's no constraint. Okay? On the other hand, what about this? Let's say we still put x is assigned to x plus 1. I only reverse the sign, right, for the equation. What would that be? False? Intuitively, what does that mean? I'm saying that is there any starting stage for me to start with such that if I try to increment x, I'm going to get a smaller value? Intuitively, it doesn't make sense, right? I mean, there's no such input. Okay? If you try to do that, let's do that very quickly. Okay, you can give the WP rule for assignments. So x less than x0 over here, x is substituted by x0 plus 1. Okay, x0 plus 1 less than x0. You're getting 1 less than 0. No way, right? False. So now the WP is simply just false, which means any precondition that's weaker than that is not going to work, right? Okay, hopefully that reinforce a little bit the understanding. Okay, that's about the assignments. Okay, you can just go over that. Okay, okay, that's exactly the formats of proof you're gonna follow. Okay. Okay, any precondition is okay. Yeah, I'll come to you. Just finish this slide here. And then false is valid but not very useful. Okay, so that means now, if the weakest precondition here is simply true, that means for your program to be correct, any precondition that's stronger than this will be okay, right? Because anything implies true. Agree? Okay. Let me summarize for you. Let me use this. When WP is true. Any precondition will be correct. Any precondition, let's say Q, will be correct because Q implies true. It's simply just true, right? Anything implies true. Okay? When WP is false, what are our options here for the precondition? Do we have any option? Actually, you do have one option. Just false. False implies false, right? Even though it's useless. Okay? I can talk about a little bit of theory as well. Okay? Only precondition false is correct. Let me make some space over here. Because false implies false is simply equivalent to true, right? However, even though it is correct, but useless. Right? Why would you have a feature where the precondition is simply false, right? What's the point? Okay. We okay? Yes, sorry, forgot about you.
So is this entire proving based on numerical values?
I would say most of the example we're going to see, yes, is based on some simple arithmetic theory. Like x, for example, x0, well, yeah, exactly. So you just see some larger than or equal to simple ones. Yeah, yeah. I would say all the proofs you're going to see either as an example or in the exam, they should be quite straightforward. Okay, but we're going to give you some challenging one as an exercise. Okay, yeah. So if you can do that one, I don't think there's any proof that can be challenging for you. Okay, yeah. I'm going to give you an exercise maybe on Friday. We haven't got to that point yet. Okay, after this. Okay, so now we talk about it. Oh, actually, this one may be interesting. So now, what is the weakest precondition for, let's say we change, you know what, actually, there's a typo over here. Can you just look at this? I should fix that. Can you look at this particular Hoare triple over here? So we got x is assigned to x plus 1, and then the post condition is very strong. X must be exactly 23. What is the weakest precondition? X is equal to 22, right? How do you calculate? You're basically going to substitute every occurrence of x by x plus 1 in x equals 23, right? You got x plus 1 equals 23, which is equivalent to x is equal to 22, right? Okay, this was easy. It's a very strong weakest precondition, right? That means you can only satisfy this. The program will only consider it as correct if the precondition is x is equal to 22. Okay, I'm just trying to play with the math a little bit. Okay, if you do the calculation, it will simply be x0 is equal to 22. Okay, anything that's weaker than x equal to 22 is not okay. For example, if you say x0 larger than or equal to 22, that's not okay, right? Let me just tell you exactly what I meant. What I meant was, let me write it down. Just look at the proof very quickly. Just make sure you're convinced. Okay, let's look at it again. Now, if this is what you're given, is this program correct? It's not correct. Okay, let's review quickly. Step number 1, you have to calculate the WP based on these two pieces of information. WP of x is assigned to x plus 1, x equal to 23. Okay, eventually you can calculate is simply x equal to 22. That is the weakest precondition. So now you want to compare this guy over here versus this guy. To be correct, it must be the case that x larger than or equal to 22 must imply x equals 22. Is that the case? If no, counterexample. SA23, right? It's going to satisfy this, but it's not going to satisfy that. Questions? Yes.
Could you give like a WP bar to show a counterexample?
No. I would say, it's in the exam, we definitely wouldn't give you something this easy. So you definitely got to show the steps. I'm just trying to give you some introduction here, right? So I would say in the exam, it would be your best interest to really show every step for calculation. So it's easier for the TA to see you really cover everything. Okay, yeah. All right. So now that's about the assignments. Now let's now talk about something that's also interesting. Let's talk about if statements. So now let's now talk about the simple case. Oh, by the way, given that you have done lab number 5, right? I hope you're convinced this structure over here is completely recursive in the following sense. We're saying that if a Boolean condition B is true, and then we're going to have some programming statements, S1. Otherwise, we're going to have another programming statement, S2. S1 and S2 over here are not precisely specified because S1 and S2 can be arbitrarily complicated. S1 can be an assignment. S1 can be a nested if statements, right? S1 can also be a loop. You can think about S1 and S2, they're of type expression, like in your lab number 5, right? So we talk about some recursive definition. So now, before I present to you the rule, what's your intuition here? I do want to talk about this particular one in a little bit more detail to give you some more insight. What's your intuition here? If I say, okay, I'll give you a little bit hints. You're basically saying if B is satisfied, I'm going to go for the branch of executing S1. If B is not satisfied, I'm going to go for the branch to execute S2. But somehow, eventually, upon the termination for this if statement here, I want to make sure R, the post condition, is established. So now, yes.
Structures as a logical formula. So
What kind of, yeah, of course. It's got to be a logical formula because WP is predicate.
B and S1 or not B and S2 implies R.
Okay, you're getting somewhere. Okay, basically you want to have like a case analysis, right? You want to say we got two cases. Either B is satisfied or not B is satisfied, right? Either way. Okay. Anyone? Anyone want to say anything further? Let's try to sketch the idea a little bit. So what we have is this, WP, and then we have if Boolean condition B, then S1. Otherwise, we have S2. Of course, you got a keyword end over here. And then we basically got two cases. B or not B. Now, in the case where B is satisfied, what do we know? If B is satisfied, then we know that we're not going to execute S2, we're going to execute S1, right? And somehow, we want to execute S1, but upon the termination of S1, we're going to establish R. But now, how do we combine these things together? Similarly, if B is not satisfied, we know that we're going to actually execute S2, but we're still going to satisfy R at the end, right? So now if I write it down, it's going to be also S2 and then R. That's kind of the very vague sketch over here. But now how do we combine them in such a way that is valid predicates? Yes? Okay, you mean B implies B and S1? You cannot say B and S1, by the way, because B is a Boolean. S1 is a programming statement. You cannot, right? Okay, that wouldn't work. Anyone? You're getting somewhere. Getting somewhere. How about I give you a little bit hints? Basically, in case number 1, you're going to somehow execute S1, hoping that it will terminate and then establish R. And we definitely can calculate W. Let me just finish this part, okay? Yeah, I know you got something, okay? Okay, let me just move this guy a little bit to here, okay? So now that means I can calculate the WP for S1 to establish R. I can also calculate WP for S2 to establish R. Okay, good, but it's not a valid logical formula yet. You still got B, you got not B, and also you got 4 different things. We're gonna combine it in a way that's logical. Let me guide you a little bit with this. How do we combine these two guys? So now we have a better ground because this is a Boolean. WP is also a Boolean. How do we combine them? Okay, you say implies. Why not conjunction? Oh, no, I'm saying the following. Okay. Oh, you know what? Okay, we got 2 options over here. Either you can say B implies, or you can say B and. Both will compile, right? But logically speaking, which one should be taken? Right? I'm just trying to tell you so you don't memorize them, right? Why implies? I can tell implies is the correct answer. But why not conjunction?
Conjunction, then it's going to depend on the end.
Okay, say that again.
So when you do implies, what is the value of B? If it's false or true, that really depends on WP and
Actually, B and actually WP, they are not depending on each other. They don't. You can see the WP calculation here only depends on S1 and R.
This can only be true when WP is true.
Not quite there yet, not quite there. Yes?
Do we use implied because they actually reach S1, the Boolean has to be true, but it doesn't matter if WP is true? Is that why we use implied?
I like the word doesn't matter. We're going to use that in my justification. Can you repeat again? I want to make sure
So to actually reach S1,
Yeah.
the Boolean has to be true.
The B has to be true, yes.
Yeah, but we don't really know if the S1 statement is true or not.
Well, remember S1 is a program. Program does not return true or false, right?
The WP is.
Yeah. The WP, not quite. Yeah, but getting there. Okay, how about I tell you. It turns out, you think about implies. If I got P implies Q, right? Think about the intuition for implies. If I know I should only worry about whether Q is true or false, if I know that P is true. Agree? Okay? However, if I know that P is already false, do I care if Q is true or false? I don't care. That's the intuition. So that is to say, implication over here should be the case because I will only care about, maybe a little bit back to what you just said. I will only care if WP here is the case or not, only if B is already true. If B is not true, that means we got to go to the other branch, in which case we don't care about this branch at all. That's why implication should be the case. But if you use conjunction, that means you always expect B to be the case and also WP to be the case. It's not necessarily. Because for you have a branching condition here, the branching condition either be true or false. It's not always the case. Okay, hopefully I convinced you a little bit. Okay, so now I have another question for you, which is even more fundamental. Now we got 2 things. Okay, basically we're saying that for this branch over here, we're saying that if B is the case, then it must satisfy the WP in order for S1 to establish R. If B is not the case, then it must be that the WP is satisfied in order for S2 to establish R. We've got 2 different cases. Now, how do we combine the 2 cases together? I heard or, and. Don't tell me implies. Implies, I can tell you it's not implies. Basically, there are options over here. Either we can say and, We can say or, we can even say implies, right? I can tell implies is not the case. And or. Or is a very intuitive answer. Oh yeah, you know my pattern, right? So it's gonna be, or is actually wrong, okay? Yeah, actually I'm very happy. Otherwise, if you say that's and directly, there's no discussion needed, right? Okay, the answer should be and. I'll tell you intuitively, and then we'll do some exercise quickly. I really want you to really remember the reasoning. That's really valuable over here. If you say or, what does that mean? That means either the first branch is going to satisfy, sorry, let me say this. If you say or, let me talk about the wrong decision. If you say it's or, you're claiming the following. I only require either this branch is going to establish the postcondition, or this branch is going to satisfy the postcondition, but it doesn't have to be both, right? But now, what about at the runtime? If I simply go to the branch that does not establish the postcondition, in that case, you don't satisfy. I'll get to that. Just a very informal wording.
What you think?
Huh?
If WP is considered Q and we don't care about the whatever it's
We do care because you can see that the programming statement we're talking about is an if statement over here, right? And this case is really like a selection. You don't really actually know whether I will go to S1 or S2, either one but not both. If I actually go to S1, it's under the assumption that B is true. If I go to S2, it's under the assumption that not B is true, right? That's why we do care. Okay. So now let's carry on with the discussion. Not here. This guy here. Okay? So now basically we have let's say we are still undecided. Okay? Basically what we have is, again, you're given the WP, right, for the if then else. We got B, we got S1, we got S2, and so we got R. We got two possible versions. Both versions, you're going to say B implies S1R, okay, not B implies S2R, the same. The only difference is here we got disjunction. Here we got conjunction. Agree? So now, I'll do that on the iPad. Let's do some quick exercise on a particular example below. And then we want to see what's the consequence if we apply the conjunction version. Oh, sorry, if we apply the disjunction version and see why it is wrong. Okay? Let me just do that. I'll let you do one of them. Let's say we're going to do this, let's say the WP rule is actually this guy here. Okay? So now, you can see here, this is B. This is S1. And this is S2. Okay? And this is R. Okay, let's do the substitution very quickly. Okay? So now, basically what you have is this. You're going to say Y larger than 0 B implies the WP for X is assigned to X plus 1 to establish X larger than or equal to 0. Agree? That's the left branch. The other branch, it will be the negation of that, which will be Y less than or equal to 0. Implies WP over here. So over here, we're talking about X is assigned to X minus 1. And then X larger than or equal to 0, the same postcondition, right? Let's now apply the wrong version. Or. Okay? Let's simplify the expression a little bit. Okay? How do you simplify this guy here? What would that be? Well, you will simply replace every occurrence of X by X plus 1. So that means you got X plus 1 larger than or equal to 0, right? Which is X larger than or equal to minus 1. Okay? So this guy over here is simply X larger than or equal to minus 1. Agree? Over here? Okay, let's do the similar consideration over here. How about here? What would that be? X, yeah, greater than or equal to 1, right? Okay, I assume you can do the substitution yourself. Alrighty, so now, if we simply use the disjunction over here, right? Let me use a different color just to emphasize that's really the critical thing we are discussing over here. So now, what can be wrong with this? Let me give you a counterexample over here. Consider the following scenario. So I'm talking about a counterexample. Okay. Let's say y is simply minus 1. And then x is simply minus 1 as well. In this case, are we going to run into trouble? We will, right? Because y is equal to minus 1, which means we'll go for this particular branch. Agree? And then in that case, x being minus 1 does not satisfy x larger than or equal to 1, which means the final post condition is not going to be satisfied. Right? Because if you simply say if x is simply equal to minus 1, and then we simply try to execute this particular S2. So that means after that, x minus 1, x will be just minus 2. Minus 2 does not satisfy the post condition, right? So we know that something's going to go wrong. However, since we use disjunction, is the Boolean expression here overall is going to be evaluated true or not? True. Very easy. Because, I tell you why it's always going to be true. Because since we know y less than or equal to 0 is going to be falsified, is going to be satisfied by this, that means this guy over here is simply just going to be true, right? Okay? If you plug in a number, it's going to be true. So true or something will just be true. Let's see. If we try this one here, if that's true, oh, actually, no, it's true. Because you can see if, because now this is, yeah, let me say it again. If you actually do this, y is equal to minus 1. Minus 1 larger than 0 is false. False implies anything, agree? Yep, it will just be true. So now, false implies anything. So this whole thing over here will just be true. True or anything will just be true, even though something might go wrong. So this is why we must use conjunction. Okay, we want to say this branch, if taken, must establish the post condition. The other branch, if taken, must be also establishing the post condition. Yeah, do think about the discussion over here, right? Of course, you can simply just memorize the rule, but I don't think that's healthy. You want to really understand logical reasoning behind. So now the conclusion is we should really do conjunction over here, so that whatever branch you take, you want to make sure really that branch is going to establish the post condition. So now I'll give you as an exercise over here. Do the same substitution over here, and now try the x, x will be minus 1, and also y will be minus 1. This case, try that and see what would it take, what would it evaluate into. I can tell you it will be false, which means that's good. It tells that there's something wrong. Okay? Guys, just make sure you get a big picture, but I think it's quite as sophisticated. Just, you got a week to study for this, right? More than a week. Any question about alternation here, if statements? Okay, so the conclusion is, after all this kind of illustration, this is the eventual rule, okay? A good news for you. We just decided that for your exam, you can bring a piece of paper, data sheets. So if I were you, I would put a rule on the paper. Okay? Yeah. I think it's fair game, right? So make sure if we ask you the proof, you know which rule to apply. Huh? Double-sided. Double-sided, US letter, no magnifier. No magnifier. Oh, I'm not sure if you see the joke. Okay. Don't put it too small. You're not allowed to bring any magnifier to the exam. Anyway, yeah. It can be typed, it can be handwritten, doesn't matter. All right. Okay, so now that's about the WP rule for this. Okay, again, the iteration is all the branches must satisfy all the branches. That's why it's conjunction. Okay, so now let's see more. So now let's, again, this is a golden rule you must remember. Okay, given any Hoare triple, and S can be alternation, can be assignment, that's what we have seen. And now, let's say we have this, okay? Let's say we got this particular program. We got this, B, S1, S2, and then R. We already know how to calculate the WP. But how do we prove this particular precondition is actually correct with respect to the WP we're going to calculate? Okay, let me show you very quickly. Basically, you want to show that Q implies the WP that we just talked about, right? What you will see on the slides will be, okay, you start with some precondition Q, and then, okay, that's the program you have, right? So you want to basically say, if you go to the if branch, that means you can assume Q is going to be satisfied. Sorry, if you go to the first branch, you know that B is satisfied. Otherwise, B is not satisfied. So you can think about, in order to prove this particular Hoare triple, one way to do it is to split it up into two possible Hoare triples and prove them individually. Okay? In the first Hoare triple here, we assume that B is the case. In the next one, we assume that B is not the case, right? Okay, just like that. Eventually, that's what you can prove. But I think that since we already explained the intuition behind why you had to use conjunction, I think that's the biggest obstacle for you. But the rest should be quite straightforward. Guys, are we okay? Yeah? Okay, you can simplify that a little bit. Okay, you can see that. But here we simply say eventually what you will have is, are you guys with me? Maybe? Yeah? Okay, good. Why don't we do one exercise together? This guy here. How about you take 2 minutes to see how far you can get to? Okay? Grab a piece of paper. I can tell you that there's something we haven't learned just yet, which is a semicolon. Semicolon simply means we're going to execute, for example, bigger is assigned to X, followed by smaller is assigned to Y. We haven't talked about exactly how to deal with sequential composition. That's the next topic. But now, given what we have over here, can you simplify that? Huh? What do you mean next line? Semicolon simply means you got to do the left before you can do the right. Right? Okay, so now, if we want to, let's say this is the question you're given. Is this program correct or not? So how do we simplify this to the extent that you have understood? Okay, let's make sure this is done, and then we talk about sequential composition quickly. Okay, and then that'll be it for today. Okay. Okay, now how do we simplify that? I'll give you 1 or 2 minutes. You can think about, again, I'll give you a little bit of hints. This whole thing over here is the Q. This whole thing over here is the R. This thing over here, everything else is the S. Right? That's a quick hint. But given that, how do we prove it? What exactly do we have to prove? Yeah, well, I don't need a final answer because we haven't really shown you how to do this yet, right? Okay, let me help you a little bit. So this is the program, and this is the post condition. First of all, let's calculate WP. WP of, can I just be a little bit lazy here? Okay, can I just say this guy here is B. This whole thing over here is simply S1. This whole thing over here is S2. Okay? Feel free to name the variables like this way, but make sure the TA can follow, okay, in the exam. If B is the case, and then we're going to execute S1. Otherwise, you do S2. After this, we want to make sure we got bigger larger than or equal to smaller. Agree? And we know that by the WP rule for alternation or conditional. How do we simplify that? Give me some help. What should I do? X bigger than y, I like that. And then? Implies, thank you. And then? Thank you, yes. And then? Yeah, okay, good. So let's say S1, just save my writing, okay? I can say S1 over here. S1 is referring to this guy here, okay? S1 is going to establish bigger, larger than or equal to smaller. Thanks. And then conjunction, right? Okay, don't forget, disjunction was wrong. That's why I discussed that, right? And then X smaller than or equal to, right? Implies WP, and now for S2, and don't forget S2 is this guy here, okay? S2, also the same postcondition. Okay, of course, the next topic will be about how to deal with S1 and S2 where we got the semicolon. We can talk about it briefly. But now a question for you. Once you have calculated this WP, is that the end of the task? Nope, what's missing? Huh? Precondition, yes. What should I do? Let's say whatever I calculate this guy here, let's say, I just call it WP just for now, okay? Whatever I calculate. So now what should I do with this WP? Huh? B implies WP? You mean the B here? Think about the B is part of the program. It has been incorporated in the WP already, so you don't need to worry about B anymore. You meant the precondition, right? Yes. Okay, so what we're going to do is X larger than 0 and Y larger than 0 implies whatever WP calculated over here. That's the second step. The blue one is the WP calculation. The pink one is, once you calculate the WP, make sure that one is not stronger than your precondition. Okay? Either prove or disapprove. Any questions? We okay? Okay, so now let's do one more, okay, quickly. The next one, okay, good. Now, sequential composition. Sequential composition exists in every programming language. Simply means you're going to execute one statement after the other. I will only go to execute S2 if S1 has terminated. Do S1 first. If that terminates, go to S2. Upon the termination of S2, I want to make sure R is satisfied. What does that mean? That means when S1 has terminated, I don't necessarily have to establish R just yet. The only thing I require is to say after S1 and after S2, R must be established. Okay? Good. So now let's work out the rule quickly before you look at the slides. Again, this particular structure over here is recursive in the following sense. S1 over here can be arbitrary. It can be a simple assignment. It can be if statements. It can also be a loops. Okay? Similarly for S2 as well. Okay? So now, how do we derive a logical formula? It's 2 o'clock? Oh, yeah. Oh, thank you. Yeah, yeah. Let's finish this, okay? Yeah, I know. Give me 2 minutes. Okay, guys, any idea? Let's do this only 2 minutes. I'll make sure I review this on Friday again, but it's good to have some challenge to your mind. Let me present it to you, okay? I know that S2 will be the last statement to execute for the program, right? Why don't I calculate WP for S2 to establish R first? And then I want to say, basically, we know that in order for S2 to establish R, this particular WP must be satisfied, right? you can think about after we have some pre-states, after S1 we have some intermediate states. After S2 we have the final states. It's only this particular final state it must satisfy R. But what about these intermediate states? The intermediate states must satisfy the weakest precondition for S2 to establish R. That's the tricky part. Okay? So that means this particular intermediate states must satisfy this. How can this intermediate state be established? By S1. You can think about the intermediate state here is the postcondition for S1. Right? So now that means we can simply do the following. Now I want to make sure S1, when completed, can establish this particular WP. And what's the WP for that? Okay, well, that's the formula. Of course, again, you can either choose to memorize it, which I don't recommend, or you can try to understand it. Okay, look at this formula a little bit more. We're going to start from here on Friday. Okay, any question for me? Are we okay? Alrighty. Let me stop the recording as I promised.